Hey there, everybody. Let's talk about your new favorite thing, which are ramps. Because I know that after the lecture yesterday, you are just loving them. So let me try and clear up some of the confusion that we encountered today. All right? So let's take a look at a good old ramp right here. Now, some things that are always going to just be with ramps. Our angle is going to be right there. All right, that is where the angle is going to be. Now let's talk about this other thing. So for motion on a ramp, one of the assumptions that we're going to make is that our gravity or our acceleration due to gravity is straight down. All right, and the reason that we make that assumption is because we talked about how in free fall, acceleration when an object is falling is pointed straight down. Well, just because we're on a ramp now doesn't mean that changes. So it's still straight down. The problem is that we are not moving in one direction anymore. We are now moving in two directions. We are moving this way and we are moving this way. All right? We're moving across the horizontal and we're also moving vertically down. Because of that, we have to work with both of those directions. But we can't work with them at the same time because those directions are independent of one another. They do not jive with each other. So what we need to do is find a way to easily work with those directions. The thing that we do with ramps is that we make one direction directly perpendicular to the ramp. Okay, we can call this the perpendicular direction or the y-axis. We make the other direction parallel to the ramp. All right, we call this the parallel direction or the x-axis. This is different from what we normally see. Normally we have this coordinate plane right here. There's that right angle. Here's my x-axis. Here's my y-axis. All we're doing is we're taking this, and I'll try to make this as clear as I can, and we're rotating it. So really we could rotate this however we wanted. All I'm doing though is taking this and rotating it so that it lines up with my ramp. Okay? If this is not clear to you, the other thing that we could do, and I'll try to make this clear, is if I took this entire thing here and I rotated it to make it seem more familiar to us. So if I took this and rotated it so that it seems like my y-axis and my x-axis are how we are used to seeing them, something like this, then maybe that might help you a little bit. All right, so I want this one to go right there. So now we've got this ramp rotated to how we would normally see it. Maybe that helps you. However, when we do this, notice that this acceleration vector still stays pointed in the direction it was originally. All right? Normally, again, a ramp is going to exist like this. So that acceleration vector points straight down. If I were to rotate it, though, all that happens is that it sits at an angle. All right? So what we want is we want everything to act in this perpendicular or in this parallel direction. So what I want to do is I want to break this acceleration vector into those components. So what we're going to do, if I can get this selected, is I'm going to show you how to do this. So here's going to be my new y component. The reason I drew it like this is so that it is in the same direction as the perpendicular or the y-axis. All right, so that's going to go right here. My x component or my parallel component, I want that to go in the direction of my ramp, which is going to be right here. So notice this is in the direction of the parallel component, and I'm going to put that right here so I can show them being added together. All right. So now what we have are my y component here. Here's my y component, and then we have my x component. And then here is my acceleration. I'm going to make that black. Okay. And again, I could rotate this entire thing to be in the direction that is sort of normal to us. Whoop. Get this to move together. Maybe. Okay, here we go. So I could rotate that whole thing. So now it looks like my y component and my x component are how we're used to seeing them. All I'm doing is just rotating this ramp. That's it. That's the big realization, all right? Now, this angle right here happens to also be right there. I'm not going to go through why that is, but you just need to accept that this angle theta also is right there. So, if none of this is making sense to you, that's okay. Here's what I need you to remember. Acceleration is made up of acceleration in the x and acceleration in the y. If we write that in vector notation, they're being added together. We could also write this as acceleration is equal to acceleration in the parallel direction plus acceleration in the perpendicular direction. Again, we have to split these into components because our motion is down the ramp. So we need to look at what is happening down the ramp. Now, let's look at what is going on here in terms of this acceleration. All right? So I'm going to erase this. Make this smaller here. Now, we've got our trig functions that we're used to using. So let's bring those out here. We know that sine of theta is equal to opposite over adjacent. We know cosine of theta is adjacent over hypotenuse. And I meant to say hypotenuse up here. Opposite over hypotenuse. And tangent is adjacent, opposite over adjacent. Okay. So I want to write my component vectors in terms of those. So here's what we're going to look at. So let's look at the y direction first here. The y direction, we've got sine, cosine of theta is equal to opposite adjacent, which is y over, or this would be acceleration in the y over our total acceleration. So if I rearrange this, I get that acceleration times cosine of theta is equal to my acceleration in the y. For the x, it's the same process, except for the x world we use sine, and this becomes acceleration in the x over acceleration, so a times the sine of theta is equal to acceleration in the x direction. Now, let's just, if that didn't make sense to you, here is what I need you to know. I need you to remember that acceleration in the parallel direction, or acceleration down the ramp, is equal to g times the sine of theta. Remember this, commit it to memory, whatever you need to do. But acceleration down the ramp is a component of the acceleration due to gravity. The reason for that is listed on this page right here, but as long as your problem is set up that way, this will be true. All right? Now, this is with the assumption that there are, wow, that's terrible. This is with the assumption that there are no other forces, which for our problems there won't be. Only gravity. All right? So you can see a lot of problems that say it's frictionless or it's on a really smooth surface. That all reinforces the fact that our acceleration down the ramp is g times sine of theta. All right? G times sine of theta. So let's look at that in a problem setting. We've got a ball rolling down the ramp, and all that is happening in this scenario is that I have a ball sitting on a ramp and I release it. All right, I release that ball. So in this case, if we're looking at motion down the ramp, that's motion in the x direction because we've redefined our coordinate system as the y direction being off the ramp and the x direction being down the ramp. Now let's call the positive x direction down the ramp here. All right, so positive x is down the ramp. And let's look at what we know. Let's list out our variables: v initial, v final, acceleration, delta x, and time. So, given this information, our v initial is 0 meters per second. We don't know v final. We don't know delta x. We don't know time. However, we do know acceleration. Acceleration, this is down the ramp, as we set up here, is equal to g sine of theta. So I'm going to put that where my acceleration goes. So last unit, we assumed that when an object in free fall is equal to negative 9.8 meters per second squared for its acceleration. Here, when we have an object moving down the ramp, the acceleration is g times sine of theta, where theta is whatever angle the ramp is at. So for us, this is going to be 9.8 times the sine of 30, which I can do that real quick. 9.8 times the sine of 30. It's going to give us an acceleration of 4.9 meters per second squared down the ramp. Now notice I called down the ramp positive. That's why this number is positive right here. So it's up to whatever you define as positive, up the ramp or down the ramp. Now, let's take out some other information here, all right? So let's say that the height or the length of this ramp from here to here, let's say that delta x is equal to 15 meters, all right? So my change of position is going to be 15 meters. And let's say that I want to know what is my final velocity, all right? What is v final right here? Well, now this becomes a problem that is just like what we did last unit. We still have the same equations because guess what? We still have a constant acceleration. Except now, that acceleration is simply a little piece of the acceleration due to gravity. That is the only thing that has changed here, is this assumption right here, is that acceleration down the ramp is g times sine of theta, where theta is whatever angle the ramp is at. So now, if I look at this problem and I want to figure out what is my final velocity, well, I need to look at what equations are available to me. V final equals v initial squared plus 2a delta x. Delta x is equal to v initial t plus 1/2 at squared. And v final equals acceleration times time plus v initial. If I look at the information that I have here, I want to know v final, and I don't care about time. All right, so if I don't care about time, I need to look for the one equation that doesn't have time in it. And guess what? That's that one right here. So at this point, I just plug in. So I take that equation, I say v final is equal to v initial squared plus 2a delta x square root, because I want v final by itself. And I get that v final is equal to 0 squared plus 2 times 4.9, because again, that's what I calculated right here, times delta x, which is 15. And I need to do plus or minus. So I get v final is equal to 2 times 4.9 times 15 square roots, which gives me 12.12. This is going to be positive because, again, we said down the ramp was positive. So the only new thing here is this piece right here. And if you don't understand the why behind it, first, let's just understand how to use it. The why will come later. We're going to keep coming back to this. This is just your first exposure to it. It's okay if you're having trouble with it right now. We've just got to practice it and get better at it. All right, guys? So apply these concepts to the problem set, and obviously let me know if you have any questions. All right? Good luck.